I think we're ready to go here. All right, so testing for two population proportions. By the time we finish section 9.5, hopefully we'll have a better understanding as how to conduct a formal hypothesis test for the difference between two population proportions. And just like with any hypothesis test, ladies and gentlemen, there's always underlying assumptions that need to be satisfied in order for the test to be valid. And there's no exception for this test. Here are some assumptions. Both samples must be random. The samples must be independent of each other. Notice independent samples. And for both samples, the sample size times the population proportion P and the sample size times the complementary proportion Q is always 1 minus P, must be at least 5. Okay, so those values have to be at least size 5. All right, obviously there's two different ways to conduct hypothesis tests. There's the critical value method versus the p-value method. Nothing changes with that. To conduct the hypothesis test, we need, of course, a test statistic, and this test statistic is distributed according to the standard normal probability distribution. So it is a z-variate. Okay. And notice the test statistic requires that we have the sample proportions from the two samples chosen from the two respective populations, minus the purported difference between the population proportions under the null statement. So as always, this should be like denoted as a little sub-zero there, because that's under the assumption that the null is true. Divided by the square root of this, this is going to be your standard error of your sampling distribution of the differences between all sample proportions chosen from the respective populations. And by the central limit theorem, the differences of all those sample proportions, and there could be thousands and thousands of them, would be approximately normally distributed. And this would be the standard deviation of that sampling distribution. It's the square root of p bar times q bar, where q bar is equal to 1 minus p bar, divided by the sum of the reciprocals of the sample sizes. Notice p sub 1 hat is going to be the sample proportion from sample 1. It's equal to x sub 1, the number of observations in the first sample that exhibit a characteristic of interest, divided by the size of the sample number 1. And of course, p sub 2 hat is the sample proportion from sample 2. Now, what's this p bar here? Well, p bar is actually going to be involving both samples. Okay, so it requires that we know how many observations from each sample exhibit the characteristic of interest, whatever that is, divided by the sum of the sample sizes. And q bar is always equal to 1 minus p bar. All right. So interesting to note that this quantity is actually required for us to be able to compute our test statistic value here. Okay, so and of course, notice that our alternative hypothesis statement determines what type of test we are conducting. And so if the difference between the two different population proportions is not equal to 0, that's a two-tailed test. Or population proportion 1 could be greater than that of population proportion 2. That'd be a right tail test or upper tail test, or um, positive tail test, if you will, and an alternative hypothesis that P1 is less than P2 is less than 0 for a left tail test there. So again, and just keep in mind that, you know, like these statements, like the first statement here, to say that the difference is not equal to 0 is to say that the population proportions are not equivalent to each other. So this implies this. Likewise, this would imply that population proportion 1 is greater than population proportion 2. And the last one would be implying that population proportion 1 is less than population proportion 2. Okay. So whether you state them this way or this way, they mean the same thing. Okay. No difference. All right. So a lot of this is like something that we've seen over and over again. I mean, we know that there's always, you know, a two-tailed test, upper or lower tail test possibility. So there's nothing new here. All right. Here's an example. 12 out of 34 randomly selected small nursing homes had a resident vaccination rate of less than 80%, and 17 out of 24 randomly selected large nursing homes had a vaccination rate of less than 80%. Can we say at the 5% level of significance that there is no difference in the proportion of small and large nursing homes with a resident vaccination rate of less than 80%? Well, to say no difference is to say that we're testing for difference versus indifference. So this would be a two-tailed test. Hence, these would be the hypotheses you would be testing to see if the population proportion from each of these nursing homes is the same or not the same as far as the vaccination rates are concerned. Critical values will be from a two-tailed test, and they will be critical Z values. And since we're testing at 5%, that means or indicates that the upper and lower tail rejection regions will receive an area of 2.5%. Okay. So 2.5% in each of these tails here. And of course, that's going to dictate what our critical Z values are going to be by using the inverse norm function. Okay, we would find our critical Z values, and they turn out to be positive and negative 1.96. So negative 1.96, positive 1.96. And the test statistic value is relying on sample evidence. So the sample 1 proportion, E sub 1 hat, is going to be X sub 1 over N sub 1, which is 12. Out of 34 randomly selected patients from the small nursing homes were vaccinated. That's 0.35. And of the 24 randomly selected patients from the large nursing home, 17 were vaccinated, giving us a sample 2 proportion of 0.71. E bar is needed for the test statistic, which is the sum of X1 and Y1, X1 and X2 rather, divided by the sum of the sample sizes. 0.5 is P bar, so Q bar would be 1 minus 0.5, or also 0.5. Okay, so there you go. We're going to need all that information to put it into our test statistic value. And when we do, we crank out a test statistic of about negative 2.70. Notice everything gets substituted in where it belongs. And again, under the null hypothesis assumption, this is 0. And that's our test statistic. Notice, ladies and gentlemen, that negative 2.70 test statistic does fall in the lower tail rejection region rather safely, being quite a bit smaller than our lower tail critical Z value of negative 1.96. Hence, we are able to reject the null hypothesis. And in plain English, we can conclude what? It appears that the vaccination rates are different between the small and the large nursing homes. That's how we could coin it in plain English. Okay. So there does appear to be a difference in the vaccination rates between the small and large nursing homes. And in saying that, we only stand a 5% chance of committing a type 1 error in rejecting a null hypothesis that may in fact still be true. Okay, so that's really not that much risk. Seems to be a rather conclusive test. And so I wouldn't be too concerned in rejecting the null hypothesis there. Okay. All right, let's see if we can do this test. That's the critical value method. Let's see if we can conduct this test now using the p-value method. So we will bring up our calculator and see what we can get into here. All right, I'm gonna have to put that over here about, okay. So we go to stat, tests, and this is going to be a 2-prop Z test. 2 proportions, we're testing for 2 population proportions, and it's a Z test. So that's the function we're going to use today in section 9.5, 2-prop Z test. X sub 1 was given back over here. That's 12. X sub 2 is 17. No, X sub N sub 1, excuse me, is 34. The size of our first sample. X sub 2 is 17, and the size of the second sample was 24. This is a 2-tailed test. Calculate. And that's how we populate our fields there, and we just calculate this, and just as we suspected, our p-value is very, very small, indicative of the fact that this is a rather conclusive test to reject the null hypothesis. In fact, we could reject the null hypothesis all the way down to a level of significance of as low as 1%, and we could still reject the null hypothesis at 0.01. So this is a very conclusive test. Notice your test statistic, which is about negative 2.666. It's pretty darn close to that negative 2.70. They just rounded off the nearest, well, the nearest hundreds, it looks like. Well, yeah, it looks like the hundreds, but it's a little off. But again, ladies and gentlemen, do you think that makes a difference? Whether you call it negative 2.66 or you call it negative 2.70? That's not going to change the location one iota. I mean, it's still an extremely conclusive test here. This will fall in the rejection region, whether you call it negative 2.66 or call it negative 2.2 or call it negative 2.95. It's in the rejection region, same conclusion, okay? So splitting hairs with the test statistic here makes no difference. Not for a test this conclusive, it doesn't, okay? Now, if the test statistic was very close to negative 1.96, yeah, then there could be a slight difference in your decision, depending upon how you round, but not for a test like this. All right, so that's the p-value method for conducting the test. It's the 2-prop Z test function. And we've seen that there's also the possibility of building confidence intervals, when you're testing 2 population parameters. And for testing 2 population proportions, these would be the formula they would use. Notice you have your difference between your sample proportions, plus or minus your margin of error. And your margin of error consists of your critical Z value, dependent upon your levels of confidence, also your level of significance, times the standard error of the sampling distribution, which is the product of the sample proportion and its complementary proportion, divided by the sum of the products of the sample proportions and its complementary proportions divided by its sample size, right, underneath the square root. Notice instead of using the weighted estimate of P bar of the population proportions, we use the sample proportions to estimate the standard error. Now, since we had P sub 1 hat is 0.31 and P sub 2 hat is 0.71, we have Q sub 1 is equal to Q sub 1 hat is equal to 1 minus P sub 1 hat, which is 0.65. 0.29 is the difference of 1 and 0.71. 95% confidence interval for the difference in the proportions is therefore I'm going to make use of positive negative 1.96 for the critical Z values. Putting everything else in, you get your confidence interval, which looks like this. And you can see that both endpoints are negative for this confidence interval. And because of that, 0 was not found in this confidence interval, which indicates there is a difference between the population vaccination rates of these two different institutions, the small and the large nursing homes. Specifically, since we did P1 minus P2 order of subtraction and we get a negative for our endpoints, that would have us believing that P1 minus P2 would have to be negative because both endpoints of this interval are negative, which has us further believing then that P1 would be less than what? P2. So it does appear that not only is there a difference in the vaccination rates between the small and large nursing home facilities, it also appears that the vaccination rates of the smaller nursing homes is less than the vaccination rates of the larger nursing homes. That's what we can also ascertain from this confidence interval here. Everybody see that there? But nonetheless, notice the confidence interval in general does support our hypothesis test conclusion, as it always should. Now, is there a way to build this confidence interval using your calculator? Well, we'll certainly try and see if there's a way. Go to Stat, Tests, and we'll go down to the 2 prop Z int function. There it is, ladies and gentlemen, the 2 proportional Z interval function for constructing a confidence interval. Hit enter. Notice since I already conducted the two-tailed test, everything has been transported automatically into this confidence interval function here. 95%, go down to calculate. And let's compare these endpoints with the ones that were computed manually. You can see that there's slight differences as far as the actual endpoint values are concerned, attributed to, gosh, I would probably attribute that to round off difference here, because these are very close to each other. But nonetheless, they're both negative, so it's the same conclusion. Nothing changes. But yeah, there is a slight round off discrepancy here. And of course, just bring it to my attention, ladies and gentlemen, in Alex, if it, complains about such an issue as round off. All right. But yeah, that's how you would construct the confidence interval then. Pretty neat. Okay. Here's another example. 68% of a sample of 200 Democrats believe that the U.S. Census is important for the economy, while only 54% of the sample of 100 Republicans believe the same. Can we conclude at the 10% level that the proportion of Democrats who believe the census is important for the economy is greater than the proportion of Republicans who believe the same? Well, this is going to be an upper tail test because we got the words greater than in there. Notice it looks like the first population pertains to the what? The Democrats, and the second pertains to the Republicans, based on the fact that P1 minus P2 must be a positive. That means P1 must be greater than P2. So there you go. Yeah, the first population is the Democrats, the second population is the Republicans. Testing at 10%. Critical value will be 1.28. Inverse norm function would help you to find that with an area to the left being 0.90. This is x sub 1, x sub 2. So notice that they are computing x sub 1 and x sub 2. Putting it in to find p bar here. And then q bar is 1 minus that. All right. Your test statistic now gets loaded up with the known quantities. So P bar again is 0.633, Q bar is 0.367. All right, everything is loaded in there. Substituted everything in where it belongs. We get a test statistic of 2.37. And notice that the test statistic of 2.37 happens to find itself in the upper tail rejection region, being greater than the critical Z value of 1.28. In fact, it is quite a ways away from 1.28, which indicates that this is a rather conclusive test, such that we would expect the p-value to be rather small when doing the test using the calculator. All right. So we have that. So therefore, we are going to reject the null hypothesis, and it looks like the claim is being supported, that the proportion of Democrats who believe the census is important to the economy is larger than the proportion of the Republicans who believe the same thing. So it looks like the claim is being supported, the claim being the alternative hypothesis statement there. Using our calculator, conducting this test via p-value method. That test 2 prop p. Hold on a second. 2 prop z test, excuse me. X sub 1 is 136. N sub 1 is 200. X sub 2 is 54. N sub 2 is 100. This is an upper tail test. And we do get a small p-value, 0.009, which is less than even 1%. So we could even reject the null hypothesis at 1%. So this is a very conclusive test. Test statistic, notice, comes out to be about 2.37. Yeah, this one's very close. Look at that. Okay. So yeah, that's your p-value method for conducting the test. Very small p-value, we reject the null hypothesis. And basically you have the same conclusion. All right, so hopefully this is making sense here. This is just emphasizing how to do things on the calculator. We already showed you. I'll tell you what, why don't we make a confidence interval here since we got this one. Let's build a confidence interval for the differences between the population portions. Go down and grab the 2 prop z int function. Everything's been imported from the hypothesis test, 95% level of confidence. And we can see that both endpoints are positive. And since we had this order of subtraction here, P1 minus P2, that difference better be a positive because both endpoints of the confidence interval are positive. which means that, yeah, the proportion of Democrats who feel the census is important to the economy is greater than the proportion of Republicans who feel the same way. So notice your confidence interval is supporting the test, the hypothesis test conclusion. Any questions about how we're conducting a hypothesis test or building a confidence interval for two population proportions here? All right, let's go to our textbook and see if we can entertain some problems here. All right, these problems are going to come out of 9.5. All right, so section 9.5 rather. Let's see. All right, 9.5. Okay. All right, we can go down to problem number 7. That'd be a nice one to start with. So let's go down to 7 here. Of course, notice in these problems 7 through 27, they want you to state the hypotheses, identify the claim, find the critical value or values, or use the p-value method, compute the test statistic, make a decision, summarize the results. All right, so number 7, let's read it here. It says, a recent study of 50 randomly selected workers ages 25 to 29 years old found that 40% have a college degree. Whereas another study of 50 randomly selected workers ages 35 to 39 years old found that 32% had college degrees. At the 5% level of significance, test the claim that there is no difference in the proportions of college degrees coming from these two different populations, which are two different age groups here, notice. And they also want you to find a 95% confidence interval for the difference of the two proportions. And so, Lazone, I would like you to conduct this test 2 ways: critical value method, p-value method, and also then find the confidence interval for the difference between these population proportions. So all 3 of those things. Go ahead, I'll give you time to do this problem. We'll call this classwork number 1, number 7 here. Classwork number 1. All right. Problem number 7 here. Comparing two different age groups of workers to see if there's a difference in the percent or proportion of those who actually have college degrees. These would be the hypotheses we're testing for. We're just testing for difference versus indifference. Sometimes we call this a non-directional test, in the sense that we're not testing to see if one's greater than the other one or less than the other one. This is just a two-tailed test. That would be the claim that there is a difference. We're testing at 5%. Two-tailed test. The rejection regions constitute 2.5% of the area of the entire standard normal distribution. Critical values will be positive, negative 1.96, obtained by the inverse norm function. Now, to compute your test statistic, there is a little bit of initial overhead you have to subject yourself to in order to actually be able to crank out the test statistic value. For instance, piece of 1 hat, they tell us, notice my population 1 is for the younger age group, ladies and gentlemen, and population 2 I chose to be for the older age group. Okay, now it doesn't matter. You could have that switched around. Okay, your decision would be the same. All right, it doesn't matter. They tell us that 40% of the younger age group do have college degrees, but we need to know what X sub 1 is. And to get X sub 1, for the purposes of computing our test statistic, we take 0.40 and multiply it by, we take 0.40, which is P sub 1 hat, and multiply it by the sample size for sample 1, which is 50. So you get 20 of those 50 randomly surveyed younger aged workers had college degrees. We also need X sub 2, which is going to be P sub 2 hat, which is 32% or 0.32 times 50, or 16 of the older age grouped workers also had college degrees. You need those values because you have to find your weighted P bar value, which is necessary for your test statistic. So 20 plus 16 divided by the sum of the sample sizes is 0.36. The complementary value of P bar, which is Q bar, is 1 minus 0.36, 0.64. Now we're able to put things into the test statistic formula here. This is P sub 1 bar minus P sub 2 bar minus the purported difference between the population proportions of the null, divided by the standard error of the sampling distribution, which is to say the square root of P bar times Q bar times 1 over the sample size 1 plus 1 over sample size 2. Dial this up, you get 0.833 about for your test statistic. Notice your test statistic falls in the do not reject the null hypothesis interval or region. It falls rather safely between the two critical Z values. And therefore, we fail to reject the null hypothesis. We cannot reject the null hypothesis. And so sample evidence is not supporting the claim that there is a difference between the percent of workers who have college degrees, whether they come from the younger age group or the older age group. There is no difference. I then conducted a p-value test on the calculator, and sure enough, my p-value is very, very large, and therefore we fail to reject the null hypothesis. The only way you can reject the null hypothesis is if you drove alpha's value all the way up to at least about 41% or higher. But then you stand a very, very large chance of committing a type 1 error in rejecting the null hypothesis. Way too much risk here. I constructed a 95% confidence interval using the 2-prop Z int function. And notice both endpoints have opposite signs. We have a negative lower endpoint and a positive upper endpoint. Because of that, 0 is definitely found in this interval, because 0 lies between a negative and a positive value. Because of that, we can conclude essentially that there is no difference between the population proportion of workers who have college degrees that come from the 25 to 29 year age group and the 35 to 39 year age group. So everything is basically complementing everything else in this investigation. And hopefully it all worked out for you. Anybody that it did not work out this way, or you have any difficulties with this? Or hopefully we're getting these numbers and everything and conclusions. Okay. All right. That was a two-tailed test or a non-directional test. Now I have one lined up, ladies and gentlemen, which is going to be number 14, investigating hypertension. Hypertension is another word for high blood pressure. It has been found that 26% of men and 31.5% of women suffer from hypertension. A random sample of 150 of each gender was selected from recent hospital records, and the following results were obtained. Can you conclude that a higher percentage of women have a high blood pressure compared to the percentage of men that have high blood pressure? Test at the 5% level of significance. And so, ladies and gentlemen, the word higher means this is a one-directional test, meaning you'd probably want to conduct an upper tail test. But I have a question for you. What order of subtraction are you going to go with? What would be population 1 and what would be population 2 if we use an upper tail test? What would we have to call population 1 and 2?
Men and women.
Population 1 would have to be what? Women or men? If we're trying to see if, there's a greater proportion of women rather than men that have hypertension. What do you think?
First one will be men, the second be women.
If we want an upper tail test, okay, where rejection region in the upper tail, then we probably want what? We want to investigate whether the proportion of women hypertension is greater than the proportion of men hypertension, because we want this to be greater than 0. Do you agree? So that'd be an upper tail test. All right. So if you want to conduct an upper tail test, you should go with the first population being women, the second being men there. All right, there you go, ladies and gentlemen. See if we can conduct this all the different ways, critical value method, p-value method, and also build the confidence interval. It'll be a 95% confidence interval. All right, go ahead and do that. We'll call that number classwork number 2. All right, for number 14, we're investigating whether the proportion of women who have hypertension is greater than the proportion of men who have hypertension. And so I called my first population of women, second population of men. So I have this order of subtraction. Therefore, it's going to be an upper tail test based on this order of subtraction I chose. That'll be the claim, testing at 5%. Upper tail critical Z value will be 1.644. This is the sample statistics for the women. 31.5% of the women in the sample chosen had hypertension. Of 52 women chosen, that means 16.38. Now, for computing the test statistic value, I did drag this out beyond the nearest whole value and reported it out to the hundreds place. Likewise, for the men sample, I also took that out to the hundreds place. But ladies and gentlemen, did anybody try the p-value method on the calculator and enter these values in as decimals? Did anybody make that mistake and do that? And then ran the test and discovered that there was an error, a domain error. Anybody do that? Because I know I fell into that trap. So you got to be careful here that when you take this problem to the calculator and conduct it via p-value method, you need to round these off to the nearest whole number. These values here, they have to be integers. So therefore, if you take it to the calculator, you need to call x sub w or x sub 1 16, and x sub 2, x sub men about 11. Okay, so you got to round these off to integers, otherwise the test will not work on your calculator. It'll give you a domain error. Okay, so these values cannot be decimals, they have to be integers. All right, anyways, computing P bar and Q bar by using our sample information. I get for P bar about 0.290. And for Q bar, I get 1 minus that, which is 0.71. I substitute things into the test statistic formula where I have women minus men here, that order of subtraction. Here's P bar, Q bar, this 1 over the number of women surveyed plus number 1 over the number of men surveyed. Anyways, I get about 0.588 for my test statistic. The test statistic falls very safely in the do not reject region, being much less than the critical Z value. And therefore, we would conclude that we cannot reject the null hypothesis. And summarize our test by saying something to the effect that the proportion of women who have hypertension is not greater and has not been shown to be greater by sample evidence than the proportion of men who have hypertension. Constructing the 95% confidence interval also indicates the same information, the same conclusion, in the sense that we have a negative value for our lower endpoint and a positive endpoint value for the upper result of this interval. And because we have a negative and a positive endpoint, that means 0 is found in this interval, which would suggest essentially that the difference between the proportion of women and men who had hypertension essentially is 0, meaning there's no difference. Okay. P-value came out to be a rather large p-value, 0.288, about 29%. And there's no way you can reject the null hypothesis with this level of risk. So that corroborates with everything else we've done here. All right. Okay. Are we getting this, ladies? Is this making any sense here? While we're conducting a hypothesis test for testing two population proportions here. Okay.
Wouldn't the n values on this problem be 150 for both?
Well, let me see here. Oh my gosh. Yeah, you are correct. So that 43 and 52 then represents the number of what? Men and women who exhibited the characteristic of opportunity. All right. Yeah, so this is all incorrect, ladies and gentlemen. I'll have to redo the problem, but it should be 150 for the number of men and women in the sample size. And the 52 and 43 are not these values at all. These would be like this would be your X sub W value, and this would be your X sub M value. That's the difference there. So, all right, I'll work this one out again, and I'll give you the results of that. But I do apologize, this is not correct here. But anybody run the test? What'd you come up with? Same conclusion or different conclusion or?
Got the same conclusion, just different values.
Wow, I'm having a lucky day, to say the least, because radically the numbers are a lot different than what I have here. But yeah, I'll work that problem out, and I'll get it to you in its entirety. All right. But I would like you to try to do another one. You can just use the p-value method for this next one. You do not have to use the critical value method. Number 18 looks like an interesting investigation. You can just use your p-value method involving the percentage of airlines that are on time. All right. It says the percentage of on-time arrivals for major U.S. airlines range from 73.8 to 87.4%. 2 regional airlines are surveyed with the following results. At the 1% level, is there a difference in the proportion of these airlines who are on time or not? So we're testing for a difference in the proportion of the respective airlines that are on time. Airline A versus airline B, whatever those are. Notice they give you the number of flights, which would be the sample sizes, and the number of on-time flights. These are the number of observations in your sample that exhibit the characteristic of interest. And the characteristic of interest is the number of flights that are actually on time. All right, go ahead and conduct that proportional test there. That's a two-tailed test. You could just use the p-value method and also build a confidence interval while you're at it. I think that would also be very useful. All right, go ahead and do that one. All right, this is the test statistic for the hypertension problem number 14, that I botched. X of W should be 52, N sub W should be 150. X sub M should be 43, N sub M should be 150. That's a P bar would be, Q bar would be this, put things into the test statistic formula. I did come up with a test statistic of about 1.02, but that's still less than the critical Z value, which is in the upper tail of the standard normal distribution. So the conclusion is still the same. We cannot reject the null hypothesis. And so again, the summarization is that there does not appear to be any difference in the percentage of women who have hypertension versus men. All right, so I did get lucky with that, but yeah, I did radically have my numbers all messed up there, but all right. All right, that's what the test statistic should be for problem number 14. I do apologize for that. Everything else remains, would remain the same. All right. This is the p-value test for number 18 for the airlines. And notice we are testing to see if the there is a difference in the proportion of flights that are on time for these two different airlines. So the hypotheses we'd be testing, the null hypothesis would be saying that the proportion of airlines A that are on time minus the proportion of airlines B that are on time, there is no difference. Versus the alternative hypothesis would be saying that there is a difference in these percentages of flights that are on time between the two different airlines, A and B. Because these will be the hypotheses we're testing, and this is the claim. We're testing to see if there is a difference between the on timeness, if you will, of these two different carriers. Conducting a p-value test based on the sample evidence that we were provided with. I get a p-value of about 0.433. Did anybody get that p-value?
Yep.
Now, this is how I populated my table, my fields rather, for this test. There it is, just using the data from the table here for the sample information. And that's how I got my p-value of about 0.433, which is a very large p-value. So there is no way we want to reject the null hypothesis here. Way too much risk of committing a type 1 error. So therefore, we would conclude that since we cannot reject the null hypothesis, sample evidence is not showing a difference in the percent of flights from airline carrier A that are on time to be any different than the percent of flights from carrier B that are on time. Essentially is no difference, okay? In the timeliness in which flights arrive at their destinations from the two different carriers. The claim is not being supported. Building a confidence interval, therefore, we would suspect what? Would we suspect that 0 has to be in the confidence interval? Yes or no? What do you think? Based on our decision regarding our hypotheses, do you think we would expect 0 to be found in a 95% confidence interval?
Yes.
Yeah, definitely. So that's so therefore the endpoints must have opposite signs. Let's go and confirm that for ourselves. Notice we don't have to type in the information again. It's just imported. 95% level of confidence. Here we go. And yes, you can clearly see that our lower endpoint is negative and the upper endpoint is positive. So with 95% certainty, 0 is found in this confidence interval, which essentially means that the proportion of flights that are on time between carrier A and B essentially is the same. That difference is the same, meaning there is no difference, ladies and gentlemen, between the number of flights that are on time for carrier A versus carrier B. Simply put, sample evidence is not supporting that claim here. All right, so today what we've accomplished is we've conducted a hypothesis test for the difference between two different population proportions. And we also found out how to build a confidence interval for those differences. And of course, the confidence intervals always were in line with the conclusion that we drew from the hypothesis test. All right, ladies and gentlemen, so I will stay on the line if you have any questions or comments or anything. If not, have a good day, and hopefully we can wrap this up on Thursday here for yet another week. And I'll try to get those things that were mentioned in the schedule. I'll try to get these things opened up, the quiz and the exam. And of course, the later I get these things opened, the later they will be due. Okay, so I will email you with the official due dates for these things and also make the changes on the schedule and post a brand new schedule updating or reflecting that change. All right, have a good day.